Alright, so in this next video we're going to put together the materials from the last video where in the last video we learned how to compute minors and cofactors. We're going to see how to assemble those cofactors together to give us the determinant of a 3 by 3 or higher matrix. We'll start with 3 by 3 and we'll work our way up, right? So the way we do this is we use what's called the Laplace expansion formula, or the cofactor expansion. Now, the official definition of the 3 by 3 determinant is that you expand along row 1. Okay, it's the expansion along the first row. So you do the 1 entry times the 1 cofactor plus the 1 entry times the 1 cofactor plus the 1 entry times the 1 cofactor, right? And now notice here I've put in that plus, minus, plus. Those are the signs that come along with those cofactors, and then these are the corresponding minors. Okay, that's the 1 minor, 1 minor, 1 minor, and those signs that are included with the cofactors, well, there's that minus sign sitting right there. Okay, the other two come with plus signs. Now, that's going to be the definition for the 3 by 3 determinant. But one of the theorems, and this theorem is due to Laplace, there's a theorem stating that although this is the definition, you can actually choose any row or column you want, and you can expand along that row or column, and you will always get the same value for the determinant no matter which row or column you choose. And because of that, if you're going to do a determinant via this cofactor expansion, you would be wise to pick a row or column that has one or more zeros in it. Why? Well, because let's say that guy is a 0, right? Well, if that guy's a 0, it doesn't matter what this minor is. You're multiplying by zeros, so you're going to get 0 for that entry. And that means you don't have to bother computing that minor, because it's going to get multiplied by 0 anyway, right? So if you get lucky, you might be able to find a row or a column where 2 out of the 3 entries are 0, and then you only have 1 minor to compute. Or, maybe there's a row or a column where everything is 0. Well, in that case, the determinant is going to be 0. Right, and there's not much to do there. Okay, so let's say I want to compute this determinant. So let's kind of do the definition first. So the definition says I should expand along row 1. So I do the 1 entry, 4 times the 1 cofactor, minus 1 to the 1 plus 1. If I delete row 1, column 1, I'm left with 1, 2, minus 1, 3. Then I do minus 2, that's the 1, entry. Okay, the 1, entry times, so minus 1 to the 1 plus 2 times 0, 2, 2, 3. And then I do 1, that's the 1, entry, this one here is that one, okay, times minus 1 to the 1 plus 3 times, can we squeeze it in? If I delete row 1, column 3, 0, 1, 2, minus 1. Okay, so I get 4. That's a plus sign, right? 1 plus 1 is even. And I get 3 minus minus, so 3 plus 2 is 5. Okay. Minus 2 times, so minus 1 to the 3, that's negative. So minus 2 times minus 1, I get plus 2. Times 0 times 3 minus 2 times 2. So 0 minus 4. And then 1. And again, this guy is positive. And it's going to be 0 minus 2. Okay, so I get 4 times 5 is 20, minus 8, minus 2, I get 10. Hey, not so bad. But I could also, if I wanted to, I could use row 2. Okay, so there's this Laplace expansion theorem that says you can actually expand along any row or column you want. So let's see what happens. Okay, so the determinant is going to be, well, there's going to be a 0. I'm not going to bother writing the minor. Okay, but 0 times the 2, 1 minor, deleting row 2, column 1. But whatever, that's going to be 0, so we don't worry about it. And then I do the 1, 1 entry, 1. Sorry, that's the 2, 2 entry. 1 times minus 1 to the 2 plus 2 times the 2, 2 minor. Okay, so if I delete row 2, column 2, 4, 1, 2, 3. Okay, and then I get 2 minus 1 to the 2 plus 3, right? That 2 is this 2 here. And now I'm going to delete row 2, column 3. Notice that you delete the row and column containing these numbers, right? It's 1 times the minor when I delete the row and column containing that entry. 2 times the minor when I delete the row and column containing the 2. So when I do that, I've got 4 minus 2, 2 minus 1. So I get 1 times 1, right, because 2 plus 2 is even. 4 times 3 is 12. 12 minus 2. And then 2 times minus 1. But what do I have inside there? I've got minus 4 plus 4 gives me 0. 12 minus 2 gives me 10. And there you go. We've got that same answer of 10. Okay. So far, so good. Now, just as an aside, we're not gonna go through the proof here. We're not gonna go through the details. But in the last video we mentioned, or I guess this was 2 videos ago, we mentioned that 2 by 2 determinants can be used to compute area. 3 by 3 determinant can be used to compute a volume. So this solid, by the way, this solid has a name. It's called a parallelepiped. I don't know who came up with that name, but that's what they call it. So this is something which you can think of as being spanned by these three vectors here. And actually, back in chapter 3, we said that one way to compute the volume of this guy is as this sort of scalar triple product. You take the cross product of 2 of those vectors, and then you take the dot product with the third. But that really just amounts to computing a 3 by 3 determinant. If you want to, that does give you one other way of doing a 3 by 3 determinant. You could compute the cross product of the 2 vectors given you row 2 and row 3, and then take the dot product with the remaining vector. That will give you a 3 by 3 determinant, but it's certainly not going to save you any work. It's going to be faster to just calculate the determinant like we did in the previous example. Okay. Now, let's say I wanted to compute the volume of one of these parallelepipeds. Well, we just pull out the result from the previous slide, which says that the volume is going to be a 3 by 3 determinant, and I simply put the coordinates in. So and by the way, it doesn't matter if I arrange these as rows or columns. Taking the transpose doesn't affect the determinant, so you do it whichever way you want. All right. So we've got our 3 by 3 determinant, and once we evaluate this, we've got our volume. We can choose to expand along any row or column that we want. I think I'm going to expand along the third row because I like that 0 sitting there. So it's going to be minus 2, minus 1 to that's in row 3, column 1. So I guess I should do it as 3 plus 1 times 2 minus 3, 0, 1, right? Deleting column 1, row 3, and then 1 times minus 1 to the 3 plus 2, and if I delete row 3, column 2, I am left with 1, 3, minus 3, 1. So I get minus 2 times plus 1 times, well, that determinant is just 2, and then the other one I get 1 times minus 1 times, that's 1 plus 9. 1 plus 9. And now you might be saying, uh-oh, that's minus 4 minus 10 minus 14. Well, that can't be right. That can't be right. Right? That's not a volume. Volume shouldn't be negative. And so really what we say is, well, that volume is going to be either plus or minus this determinant, depending on how things come out. The right answer for the volume here would be 14, right? Now, the reason we don't worry about that sign, aside from obviously volume should not be negative, is that the sign is going to depend on the order in which we write down these numbers. One of the properties of the determinant, which we will see fairly soon in a later video, is that if you swap rows in the determinant, right, that's one of your elementary row operations, is swapping two rows. If you swap two rows in a determinant, you get a minus sign. And so if I had decided to write the 301 vertex down before the 1, 2, minus 3 vertex, I would have got plus 14 for my answer, and I wouldn't have had to worry about the minus sign. So if you're doing one of these volume computations and you get the wrong side, you don't worry, you just change the sign because you know that volume should not be negative. Okay. Now, how do we go from here to 4 by 4 and higher? Well, you take the same definition, right? I know I've used summation notation. This is A11 times the 1, 1 cofactor, A12 times the 1, 2 cofactor, and so on down to A1n times the 1n cofactor. Okay, so what you do is, if you have a, so let's say you had a 4 by 4, right? 2, 1, 0, 3 minus 1, 1, 2, 1 minus 1, 2, 1, 4, 1, right? Well, you would do this when you would go across the first row, and you'd say, okay, it's going to be 2 times the 1, 1 cofactor plus 1 times the 1, 2 factor plus 0. Well, we won't worry about the 0, and then 3 times the 1, 4 cofactor, right? And then each of those cofactors, well, I can put in my signs, right? So this one, 1, 1 is positive, so I can say, well, that's going to be the minor. 1, 2 is negative, so I could make that a minus sign and do the minor. 1, 4, again, 1 plus 4 is odd, so the sign factor there is negative, so I can make that a minus sign and do the minors, right? And so then you would get, so it would be 2 times, so now I got to delete row 1, column 1, so if I do that, delete row 1, column 1, I've got 1, 2, 1, 3 minus 1, 2, 1, 4, 1, right? And then I subtract, so if I did row 1, column 2, I'd be left with minus 1, 2, 1, and then 4 minus 1, 2, 0, 4, 1, and then minus 3 times, I'm barely going to make it in, times this last guy, right, minus 1, 1, 2, 4, 3 minus 1, and 0, 1, 4, and then we say, all right, well, we know how to do a 3 by 3 determinant, so we can calculate each of those 3 by 3 determinants. We put them back in, and then we've got the 4 by 4 determinant, right? And so you might be getting the feeling that this is a lot of work. Imagine you're using 5 by 5 or high, like 5 by 5, you're going to get 5 4 by 4 determinants. Each of those 4 by 4 determinants is going to be done in terms of 4 3 by 3 determinants. Each of those 3 by 3 determinants is 3 2 by 2 determinants. Geez, that sounds like a lot of trouble, right? So how do you save yourself some work in general? Well, one way is, you hope you've got some zeros, right? And if you do, well, then maybe it's not so bad expanding. So in this case, we would get 1 times, so the sign factor in the 1, 1 spot is plus 1, and then 1, minus 1, 0, 2, 1, 3, minus 1, 4, 2, 0, 0, minus 2. That's in the 1, 4 spot. The sign factor is a minus 1 times. So if I delete that, I'm left with 3, 1, minus 1, 0, 2, 1, 1, minus 1, 4. Okay. And then I calculate each of these 3 by 3 determinants. And so the first one, again, I just have a 1, so I'm going to expand along the first row. I get 1 times 1, 3, 4, 2, subtract minus 1 times 2, 3, minus 1, 2, and then I've got plus 2 times. So for the second one, I'm going to expand along the first column. 3 times 2, 1, minus 1, 4, plus 0, plus 1, minus 1, 2, 1. Okay, all right. Those came from the 1, 1 and the 1, 3 positions. Both of those get plus signs. By the way, notice that when I get down to computing these two minors, right, these 3 by 3 minors, right, the sign factors that I use are the sign factors treating this as a 3 by 3 determinant in its own right. I don't go back to the original matrix and figure out what row and column these were in originally. I just look at the rows and columns that they're in now. Okay, and so now it's a matter of expanding. 2 minus 12 minus 10, that's going to be a plus sign. 4 plus 3, so minus 10 plus 7, plus 2 times. So here I've got, so this is going to be 3 times 8 plus 1, 3 times 9, and then the other one is going to be 1 plus 2, so 3. 27 plus 3 is 30, times 2 is 60, minus 10 is 50, plus 7 I get 57. Okay, not too bad, but you can see how this could very quickly become a lot of work, and so you might start thinking, well, there must be, you know, a better way of doing this, right? And let's leave that. I think we'll leave that out. Maybe I'll pause there for a second. So what we're going to see in the later videos is that you can simplify determinants. The way to simplify your determinants is you first figure out the effect of row operations. Say, what happens if I do a row operation to my determinant? Does that change the value? And if you know what happens, well, you can use row operations to create some zeros, and then it's going to make it easier for you to expand. So we'll see that the way to do a large determinant efficiently is you use row operations to simplify, and then you take the determinant, because as we can see here, right, having these zeros is convenient because it means instead of having to do 4 3 by 3 determinants, I only had to do 2. Now, this last slide, I'm just going to leave this here. You can pause and look at it if you want. This just gives you an idea of where determinants come from. Where does the formula come from? It comes from trying to understand, you know, general systems of equations. If you write down a system of 3 equations and 3 unknowns with an arbitrary coefficient matrix, and you kind of work your way through and you try to figure out, you know, what the solution should look like, and what condition do you need to guarantee a unique solution. I mean, you can see here, right? If I want to get a leading 1 in that second column, I need to make sure that that quantity, AD minus BC, which is the determinant of the original matrix, I got to make sure that's non-zero. In the 3 by 3 case, you find the same thing. If I want to guarantee a unique solution, I got to make sure that the determinant of the coefficient matrix is non-zero. And so as far as systems of equations are concerned, you know, the formula for the determinant really, you know, relates back to systems of equations, and determining whether or not there's a unique solution corresponds to determining whether or not the determinant is 0. So you can find that this determinant computed via this cofactor expansion, it does give you this answer about whether or not the solution to a system is unique. Okay, that's it for this video.